Well, welcome everyone. Thank you so much for being here. This will be a lot of fun. I'm Kate Rooney. I'm a reporter at CNBC. I mostly cover tech and fintech, a little bit of quantum lately, but I'm by no means an expert. And these are the experts, so I'll let them really steer the conversation here. And I think we'll do some audience Q&A at the end, but I'm sure all of you are real experts, so feel free to jump in, and we'll leave some time at the end for questions. But Robert and Nick, I'll actually have you guys do your own introductions and walk through your professional backgrounds, but that'd be great to maybe give the audience a sense of kind of where you started your careers and how you ended up at Samsung and Google. So Robert, maybe we'll start with you.
Sure. So I'm in Samsung's what we call open innovation team. It's kind of a mix of strategy, technology scouting, and also encompasses things like university relations. And I'm affiliated with our corporate R&D lab that's geared toward more frontier research called the Samsung Advanced Institute of Technology. I've been there supporting this SAIT, as we call it, for about 10 years now. I've covered a broad variety of technical topics, mostly around materials, a little bit around computing. My background's in chemical engineering, so not the quantum physicist that I probably should be to be really understanding this topic, but I have a lot of experience in looking at different types of advanced materials. So some of the things that we've looked at in the past have been battery materials, things like display materials, QD, organic LED materials, films, and various optoelectronic materials. So I think these materials provide an outlet for quantum computing in Samsung alongside many of the other advanced computing things like AI and optimization that we could likely use on the business side as well as the research side.
Not a quantum physicist. That's you said that as if, oh God, I can't believe.
Yeah,
I know.
Terrible.
Embarrassing. Well, I should also say this will be about sustainability. So we'll talk about battery tech, and maybe we can come back to you on that. But Nick, let's get your background and how you got to Google.
Sure. So I work at the Google Quantum AI Lab. I'm a research scientist there. I work on the algorithms team. And so in short, what that means is I figure out what we're going to do with quantum computers now, I guess in 5 years and 10 years and beyond. And so some of that work involves running experiments on these devices. Some of it also works on complexity theory type work and seeing how particular problems that chemists such as myself might be interested in are going to scale. Let's see. So I've been in quantum computing for about 3 years now, 5 years. And before that, I was in traditional quantum chemistry. And so the goal of quantum chemistry, of course, is to simulate nature. And it was actually a pretty easy transition over. And so I think that before that, I was in my PhD, and we worked on developing mathematical methods for solving chemical problems. And so I guess I'm squarely in the expert category for this. So I can hopefully provide maybe realistic color to some of these.
We will definitely lean on you for that. Robert, I want to go back to the battery tech you mentioned, and we can get to some of the real world use cases and what both Google and Samsung are working on. Maybe you can walk us through that and sort of your experience in battery tech and how quantum is getting applied there.
So, I mean, I think it's worth going back 10 years or so. Batteries, this was around the time the iPhone came out, right? We had lithium-ion batteries, pretty good. That's part of the enabling factor, along with all the computational advancements that led to the smartphone. Batteries really haven't changed much since then. They've gotten better. A few percent a year is typical with the lithium-ion battery. You improve the cathode, you improve the anode, you add a little bit of silicon, things like that. But ultimately, it's not been a big change. The big changes people are hoping for in that space are, for example, adding silicon to make the complete anode, which would increase the energy density. And then, of course, the thing that's been hot recently, and the markets at least, have been solid state batteries. We've had a number of companies go public, QuantumScape being the most notable one. Solid Power, I think, also just got its SPAC merger approved. But these are companies that are trying to develop the next generation of batteries that'll be both, safer and ideally and ultimately cheaper because you have less materials. Essentially, you don't have an anode. But there's a ton of challenges to this. These companies, they presented data, which is great, but there's a lot of practical challenges with getting to a long battery life that, you can make football field sized, areas of these without defects that are going to cause them to fail in the real world. And there's a lot of underlying computational challenges in chemistry and in sort of the engineering of the cell structure that are really challenging. Particularly with solid state batteries, you need to find a material for this solid state electrolyte that can conduct ions. It has to be chemically stable against the anode and cathode, and it has to have the performance characteristics as well as be synthesizable. And we internally do a lot of classical computational chemistry to try to discover these materials, but it is a challenge. And that's certainly one area where quantum computing could, in the future, provide a benefit, is giving a more specific answer to, is this solid electrolyte material reactive with lithium? What does that interface look like when the reaction happens? Is it self-limiting? Does it keep reacting that is then detrimental? And on the cell level, I think some of the multi-physics models that incorporate electrochemistry, possibly mechanical stress strain models, and even fluid flow if you're dealing with certain types of batteries, are really challenging problems that could ultimately use quantum computing if quantum computing is proved useful for things like solving linear systems of equations or sort of similar approaches that would be relevant there.
Got it. Yeah. So that is definitely one use case. I'd love to get both of your takes. And maybe Nick, we'll go back to you on this one. The big picture, most exciting applications you're seeing in sustainability with quantum, what are some of the big issues that could be solved here?
So I think the way that I view quantum computing is kind of from the lens of a chemist who tries to simulate some of these systems. And so I have kind of this view that quantum computing is a CAD tool that really, just like any other computer program, that's helping a human design a chemical system. So it requires expertise in many areas. And maybe, like Robert said, it lets you kind of simulate something with just enough accuracy beyond what we currently can do to answer some important questions. Some of those areas, of course, I think one that's been really kind of highlighted in our field is nitrogen fixation. So that's a very kind of fancy name for making ammonia. Right now, that's a very expensive process to do. But there are lots of other things, like even making aluminum is actually quite expensive as well. And so there are things kind of along the way that really people with chemical engineering backgrounds are the driving force. And I think the idea of quantum computing is that we can actually provide a tool to help that design process be more powerful.
Got it. No, that makes a ton of sense. And what about, so Robert, anything you're seeing? I know the battery side of it is, I'm sure, long-term, probably a big way to move the needle on sustainability. What are you seeing from Samsung?
Yeah, I think, just bigger picture than Samsung even. I think there's a lot of potential in the long term. I think quantum computing has to live up to its promise, and we may not know that for a while. But if you think about the way companies more broadly are trying to address sustainability today, which includes looking at their supply chain, looking at their logistics, their carbon footprint associated with getting goods they need to go where they need to go, or computing is a big one these days. What's your computing footprint? I'm sure Google cares a lot about this, right? So I think in addition to developing the new materials, so in terms of logistics and operational efficiencies, you can imagine that optimization, solving complex optimization problems could provide improvements there. In terms of the material side, I think there's also a big opportunity for designing new catalysts that may provide future solutions to how to, nitrogen fixation is one, how to convert carbon dioxide to high value or valuable chemicals to give more economic incentives to, the direct air capture technologies that are, not very economical in our current understanding. And I think in the catalysis side, that if you can really have solutions, basically porting what we know about computational chemistry today and enabling higher accuracy computations that give you more confidence in these new catalytic materials. You could apply that to all the places catalysts are used today, which is, in creating millions and billions of tons of commodity chemicals and other things that would reduce energy usage in those industries. So there's a lot of kind of baseline impacts that quantum computing will have that if you sort of play them out over entire industries could have a significant impact.
And how hypothetical is this? Are these things that are being worked on right now that are being fixed, or are you saying, oh, okay, this is a long-term problem that could be solved? And Nick, on the Google side too, are there certain things that you've said, okay, we figured out a way to do this, we're actually working with X company and helping on sustainability, or are these sort of optimistic, more long-term goals?
They are long-term goals, they are optimistic, but they are realistic. And so one of the things that my team does is actually we have research partners who are in academia and in industry, where we'll work with them on particular problems that are affecting, well, it seems silly as a kind of theorist to say their business, but at the end of the day, it's a calculation that we're doing.
Right.
And we're working on kind of what are the sizes of the quantum computers that we're going to need to build to address those types of problems. And so it feels very realistic. And we also go actually one step beyond that, where we actually try to use the best classical methods that we can to actually address some of those issues.
And actually, to stop you there, are there things that you found in your research that you say, oh, we could actually use classical computing, we don't need a quantum computer?
Oh, absolutely. So
how often does that happen?
Not that often. I mean, I think the community generally agrees that a lot of these problems that we actually get exposed to are pretty challenging. We might make headway in a different area, but most of the people that we're interacting with are very talented in their particular areas, and they know about these problems more than we would.
Got it. So you've had to pivot in certain areas and say, oh, we could actually solve this in the near term?
Yeah, so in some sense, it's about defining kind of a boundary between kind of classical advantage and then quantum advantage.
Mm-hmm.
So like, what is that near-term boundary for maybe a device that we could build in 10 years, a device that we could build in 20 years? Those things might actually look very, very different.
Right.
And so we have to bring to bear the best classical methods possible to actually even define that question.
Yeah, let's talk about some of the milestones. I mean, 10 to 20 years in tech feels like forever when things are moving so quickly. What are some of the near-term milestones you think in quantum when it comes to sustainability? What can we expect, maybe the next 5 years? And I would love to get your take on sort of the near-term landscape.
Yeah, I guess probably the biggest one, and I think Google's been putting a lot of effort here, is demonstrating a decent error-corrected logical qubit, as they call it, which will fundamentally be the building block to creating the more powerful, longer-term future quantum computers that will be able to potentially solve a lot of the problems we were talking about earlier. And we've seen a number of companies sort of throw their hat in this ring of let's start to try to make small logical qubits with the relatively small quantum computers that we have today. And I think that's going to be an important project to work on over the next, say, 3 years. I'm sure you can expound on that a little bit.
That's definitely a good kind of exposition of it. Yeah. So we have this like long-term roadmap. Long-term as in 10 years.
Yeah.
And there's certainly milestones from a hardware perspective along the way. There's demonstrating an error-correcting code. There's demonstrating a scalable error-correcting code. There's demonstrating like a logical, or maybe like the forever qubit, one could kind of say. That would be like the smallest possible version of a quantum computer. It's one logical qubit that lasts effectively forever. And then, scaling that and turning that into a real engineering problem. But there's a bunch of physics that we want to de-risk in the meantime, and some of these milestones are actually set up for that. In terms of the applications, I think, this is actually where we take input from the classical computing community and research partners that, about which are interesting problems to address at what particular scale. So we do experiments kind of on near-term machines that are, I think most people would say, are very small and more of a demonstration. But the idea is that each of those pieces is telling us about the hardware and then how we might be able to translate that information kind of into larger experiments along the way. So there's a little bit of it's a little bit of a random walk, but we definitely have a bias towards like what we want to do with these machines going forward.
And how does that differ from other big tech companies working on this? Are there different approaches when it comes to quantum? And how would you describe, what Google is doing versus Amazon or Honeywell or any of these other big players?
For sure, there are big differences. Certainly, Google's main effort is all about scalability. And so we're very interested on making superconducting qubits right now, but we're open to other technologies if they can be demonstrated that you can build one of these 1 million, 2 million, 20 million physical qubit devices such that we can actually run the error correction that we need to implement some of these algorithms that actually have exponential speedups. I mean, exponential speedups are like the thing that is driving everything forward. If we're talking kind of a high order polynomial, it's a bit harder to justify spending, billions of dollars to build one of these. But actually, certainly in chemistry and and materials physics, that exponential speedup is there, and so that's actually nice.
Got it. And Robert, anything to add on that in terms of the different approaches you're seeing?
No, I think it's good that we're seeing so many different approaches. They were talked about earlier today, obviously, and I think the bottom line is we don't know which one or multiple ones might yield a practical quantum computer that can solve a quote unquote real problem that people care about in industry. Google's doing great work, IBM's doing great work, IonQ, Honeywell, a lot of the startups are all doing really interesting stuff, and nobody can tell you, well, this one's going to be the one that can scale. I mean, we have a lot of evidence that superconducting has a big chance of that. Ion traps have proven that they're pretty good. But ultimately, I think it's good that the community is taking a somewhat scattershot approach, and hopefully, for the benefit of the world eventually, one of them will hopefully come out and show that we can build this giant error-corrected quantum computer that we think we need.
And what are some of the challenges along the way, especially to kind of bring it back to sustainability? Are there any big headwinds or obstacles in achieving some of this near-term great, some of the outcomes that we really would benefit the world? Like you're saying, what are some of the biggest challenges in applying quantum to some of these big issues?
So in my experience, it's actually been distilling it down to a computation that helps answer a physics problem related to sustainability, related to batteries or something like that. Generally, that is, a big effort in research science and engineering, and kind of being able to articulate something like that for that then a quantum computer then can go calculate is usually a huge effort. And so, like I said earlier, part of what we do is actually try to evaluate, how can we answer this classically first, which informs how we might actually go about using a quantum computer to address that question, and then only then go do the resource estimates on what will this cost and things like that. And so for the nitrogen fixation example, that's something that the field has really been chewing on for like 5 years now. And we've seen kind of run times for those, or theoretical run times for those, come down from like unknown to, a couple of days. And so that's been very serious progress. But we only have that progress because we knew at first, at least, the type of question that we could answer. And so that's kind of the trajectory that one would take as like an intermediate type of question, defining those and going out and saying, okay, here are the kind of the challenge problems.
Got it. Well, a bigger question on sustainability and for the industries themselves that may be disrupting their own businesses by solving some of these issues. Are they the ones coming to you guys, or is it the researchers saying, oh, we actually found a great solution for whether it's carbon capture or something to sort of improve what they're already doing? How are you working with the industries that may be disrupted in the process of actually getting to some of these solutions in quantum?
I think a lot of the industries that at least that we work with are knowledgeable of quantum. They already run a lot of quantum computation. They know it's important to their, or not quantum computation, classical calculations of quantum physics. And they already know that's important to their business. And so they see, okay, this is a new technology that has this promise of exponential speedups under certain conditions. Let's go find out what those are, and if that's something that actually we will have to pay attention to in the future.
And what are some of the industries?
We work with chemistry companies. We work with materials companies. Really, my domain is in physical simulation, and so kind of those things that are related to simulating nature, especially chemistry and materials. But we do resource estimates for cryptography and things like that. I mean, our group has put out papers on what it would cost with a quantum computer to break Shor's algorithm, or using Shor's algorithm to break encryption. It's 20 million qubits on kind of our best estimates, and so if we can only break encryption with quantum computers, that would be very boring. There's like a lot of much more interesting science that can be done with these devices.
Got it. Well, to bring it back to the battery conversation, are you seeing any movement on whether it's the auto side? I'm sure that also has implications for Samsung's businesses with batteries. What are you seeing on that side?
I think that right now the companies are not thinking about it in use of batteries. There's a few small examples of doing really toy problems. I think one of the challenges with batteries and with, for example, semiconductor materials and catalysis is that a lot of the work that's been done today, in Google and elsewhere, has been somewhat focused on sort of isolated molecules. And that works well for, things like gases and liquids and for maybe biological molecules to some degree. But a lot of the battery and semiconductor and catalytic computations are done on a solid. And these require typically a different approach. I mean, Nick can, I'm sure, talk about that, but there's been a lot more emphasis on these small isolated molecules because that's where I think the most potential is in the near term. The large sort of periodic materials that might go into a battery or catalyst, they oftentimes require potentially a lot more qubits, at least in our current knowledge.
Got it.
And so that's something that I think the research community, it may not be appropriate to focus on that now because it'd be a little bit like spinning your wheels. You're a little bit early, but that's a direction that it needs to go in to solve a lot of the important problems in batteries or semiconductor catalysis.
And are there areas of sustainability you think that are not getting enough attention right now? That something like batteries might be the more obvious problem here, but any sectors here that really you think are underrated or just not getting enough attention?
Yeah, I don't know. I think just in the quantum computing field, I think it may be something like catalysis and maybe alongside catalysis, you could think about things like adsorbents and other sort of boring stuff that goes into these giant chemical processes that feeds our lives every day. And there's a lot of impact that you could have by improving the efficiency of these processes by a few percent. It's kind of like the nitrogen fixation problem too. A lot of the world's energy goes into actually making that to make fertilizer to feed the world.
Yeah.
And it's similar. We consume a lot of oil, we consume a lot of plastics. All of these things have a lot of chemicals, catalysts, and other things that ultimately require a lot of energy to make. That could be impacted if we can develop these solutions.
Got it. What about you, Nick? Anything that's underrated in your opinion?
I don't know if I could put my finger on one particular thing. I usually take a slightly more abstract perspective, which is, if we can accelerate some of these computations. I mean, I particularly like catalysis. That's one of my favorites. There's great examples of being able to do very exotic chemistry that certainly sounds like you could be able to make very expensive feedstocks much cheaper. But unfortunately, they involve like iridium, which is one of the most expensive metals on the planet. And then there's a lot of research into how to just use iron, which is, abundant in the Earth's crust. And so I have this higher level view. I don't know if there's any one particular thing I could mention.
Got it. And both of you are working at private companies that I would assume have a decent amount of financial backing for these projects. Any thought on the U.S. and global competition, the U.S. having most of the funding and research being privately funded versus you think of a place like China where a lot of it is government funded? Any thoughts on sort of the broader financing of some of these projects and if the U.S. is at an advantage or a disadvantage versus the rest of the world?
I don't know. I think in general, right now, it feels like more funding is better, wherever it happens. I think contributions to the scientific community and the sort of fundamental level research we have now are coming from all over the world. And so any additional funding is great. I think, and we see it in some of the legislation that's trying to be passed, that, extra money in the US on quantum computing and AI and some of these sort of national security related, technologies is probably coming down the line. I think that's good. And certainly other parts of the world are going to be putting money there. So I think the US has what I think is an advantage right now, just in terms of our talent and our ecosystem, but we can't take that for granted.
Yeah. Nick, what are you seeing?
The US certainly hasn't always funded quantum this heavily. And I think now is a great there's a lot of money in the ecosystem. I was thinking about what I was going to do after graduate school, and that seems long ago now, but it certainly wasn't obvious what to do with a degree in quantum anything. And so there should probably be a structured strategy on how to actually divvy up responsibilities between industry and government. There's a lot more government money now, and so things like more risky qubit design and things like this, and technologies that are harder to actually spend a lot of time on in an industry setting, is, I think, a very good division of how you could actually allocate money and people power.
And you mentioned some of the risk. Is there a risk that some of these things just don't work out completely, that they are, in some sense a failure, but also probably you will have learned something in the process? How do you think about that as part of your day job, potentially working on something that doesn't work out?
Well, I try to straddle this line between classical chemistry and quantum information, so I'm always safe. But I think if the worst thing is that we learn about quantum computing and quantum information and the nature of humanity's most accurate theory ever discovered, and so that doesn't seem so bad. And there will be other technologies that are developed along the way. Better dilution refrigerators, better sensors, better control electronics, all of the things that actually go into a quantum computer and don't just look like that kind of chandelier looking thing. Mm-hmm. All of those technologies can be transferred to other areas. And so, in the end, if there's something that happens that causes a breakdown of our knowledge of quantum information, then I think, maybe that's pretty good, because then we'll know. One of these things actually happened when we were doing the quantum advantage experiment 2019. There's this plot that we have where we're going to larger and larger qubit counts, and the fidelity is slightly going down, and there was this kind of precipitous drop. And some people in our group were making some jokes like, oh, maybe quantum mechanics is actually broken. Of course, no, it was not. The experiment confirms what we think is happening. And so if at the end of the decade we've run the gamut of these experiments, I think that's a very validating thing for quantum mechanics in general. Got it.
Robert, what's your take on that?
I think pretty similar. There was an Air Force research lab talk this morning that sort of showed there's not just quantum computing. There's this broad portfolio of quantum information science enabled technologies that might be deployable, from communication and sensing and computing, and timing is one that they care about a lot with GPS and atomic clocks and things. And maybe one way to think about this sort of race to build a quantum computer is it could be a little bit like the space race, in the sense that, like Nick said, there's a lot of underlying technologies that go into enabling these, that things need to be higher precision than they ever have before. They need to be just different and new, and these ultimately may find use cases and other things outside of quantum computing. I'm optimistic that someone in one of the qubit or quantum computing modalities that are being tried will find a way to scale it and to give us, these million qubits or whatever we may need to solve real problems. So I think that, it's good that there's this variety of technologies being pursued and a variety of underlying foundational technologies that'll probably find use elsewhere.
Got it. I think we may be running up. If anyone has, start getting your audience questions ready. But final question for me on climate change and just the environment in general. That seems to be one of the more immediate risks, and doesn't feel like it has 10 or 20 years. Are there things being done in the near term, whether it's carbon capture or any of these technologies that you're seeing that may be, good news in the face of what we're seeing in California with all of these wildfires and just some of the near-term risks that we're seeing all around the world?
That's a tough one. I certainly know at Google there's a lot of research in this particular area. It's something that the company really does care about. Definitely from the machine learning side. On the quantum computing side, we do a little bit of less of that, but we certainly look at things like if one was to simulate weather or was to simulate maybe some of the relevant phenomenon, what would be the cost and things like this. And so it's certainly something we're paying attention to and understand that it is a pressing issue.
Got it. Any final thoughts on
I
that?
guess, it would be a mistake to think quantum computing will be our climate savior.
Yeah.
There's still a lot of uncertainty. It could have important applications, like you said, in climate modeling. These sort of models that the IPCC always run to try to predict these long-term weather patterns and temperature rise and things that hopefully are going to find their way into our government policies. Those could be important applications, but I think it's unlikely that we will have a quantum computer that can do that for quite a while. And so we should just double down on all the classical stuff we know how to do and pursue many of the technologies that are there that can get us a good way down the sustainability road.
I agree with you there. Well, guys, let's open it up. I'm sure all of you guys have smart questions. So if you've got any, I don't know if we have a mic going around, but if we have any audience questions, we can.
So I very much believe in the theory of error correction in that its predictions have been validated thus far. And so I don't see any reason why we wouldn't be able to scale the devices to the sizes that we needed to, and then also generate the resource states that we need to actually perform Shor's algorithm. So I think there's nothing, as far as I can tell, standing in the way of that, other than getting to the error rates that would be required to actually run those algorithms. So there's a question of whether we believe the error rates can be lowered sufficiently to run the surface code, which would require 20 million qubits. But of course, that's only going to break, 20 million is a number that is going to break RSA at 2048. And so someone could always increase the bit nonce and make it more secure. For hybrid, I think it's a much more difficult thing to pinpoint how that will be useful. Personally, I think the road to determining that actually looks a lot like the error correction development cycles. So it's likely that we need fast feedback, the same with error correction, algorithms for, or devices that actually have high quality qubits. And so I think those roads are actually very parallel. And so pursuing both is kind of a useful strategy.
Got it. Anybody else? Sure.
Yeah, I guess to start it, I think the good thing about all this is quantum computing is kind of the foundation of these hopefully future developments. And just the way that classical computing is used by the companies that make today's nitrogen fixation catalysts or today's catalysts to do hydrocarbon cracking or whatever they might use it for. There will be economic incentives if and when this quantum computing is available to design better catalysts for the companies that supply the catalysts to the big companies that make these things to actually do it. They will want that competitive advantage. And so I think there's a natural reason why these technologies would proliferate in a good way. And it could mean that a chemical company may need to redesign their process. It may not just be, plug this catalyst in this packed bed. It could be more expensive than that, but the potential benefits could be such that it's definitely worth those kind of investments. And I think that's a hope that we have, that if you can do better chemistry, maybe we find better ways to do classical chemistry, quantum-inspired classical algorithms or something, that quantum computing kind of gets people thinking. It's happened in some fields already, I guess, that these will then feed in and sort of help in a broad way.
Any thoughts on that, Nick?
I think that mostly covers it.
Yeah.
I kind of agree with everything. I think that it's likely that there will be a kind of need to be a coupling of economic forces and policy to kind of guide using, to kind of incentivize some of these companies to actually, maybe invest in making some of these green technologies usable, and then maybe even investing in developing them, because the development cycle can be very, very long. But I don't think ultimately that will be passed up. I think if you can get around having to spend more money to, $1 billion to build yet another, very expensive factory versus investing in technologies that might lower your costs in the future, I think that's something that people are very motivated to do. It's just whether the policies are helpful in achieving that.
That's a great question. I think the real world application and the possible innovator's dilemma of sort of cannibalizing your business near term for what can be a longer term outcome and long term beneficial for the world. We probably have time for one more question if anybody's got a good one. The podium might be blocking. Well, if not, fascinating conversation, guys. Thank you so much for being here, and thank all of you and for the great questions. Really interesting topic, and more to come, I'm sure. So thanks a lot. We'll hand it over to the next panel.
Thank you.
Thanks, Kate.